Good morning, class. We have the last lecture lined up for machines today. Okay, so recently we have been discussing pulleys. Okay, and in pulleys we had discussed single fixed pulley, single movable pulley, compared them. Then we moved ahead onto the combination of pulleys. We did block and tackle system and the various possible combinations in that also. Okay, and we also solved a few numericals based on pulleys. Now we are coming to the last part of pulleys, where we will discuss one particular example, that is one particular question, unsolved question, that is given in your book as a part of the exercise, which I have discussed over here, written over here. Okay, so we will solve this together over here, and I'll tell you how the marks are to be allotted for such questions in your board examinations. Okay, and then obviously we will discuss that one last case which is left, in which we will have one fixed pulley and a number of movable pulleys. Okay, so let us first concentrate on the question at hand. We have, you can read in the diagram given. Okay, so this is the diagram that they have given. Okay, how many strands of tackle are supporting the load? So when they say in the diagram, this is the diagram that we have. You can make out that this is a block and tackle system, which comprises of two blocks. Okay, this upper block and the lower block, and both blocks have two pulleys each in them, and the direction of the effort is downward. So that is the information that is given in the question. Now let us read the first part again. How many strands of tackle? So tackle is the rope, I have already told you, and strands means the parts of the rope or the parts of the tackle that are supporting the load. So let us look at the diagram. This is the load, and load obviously is going to pull everything, try to pull everything down, okay, in this direction. So what are the strands or the parts that are supporting this load, directly or indirectly? So you see, number 1, number 2, number 3 and number 4. So 1, 2, 3 and 4 strands are there. Okay, so when you will write the solution, you will write like this, solution, and you have the first part, answer to the first part, you will write 4. Okay, then moving on to the second part. Okay, mark capital T in all the strands. Okay, so in all the parts that are there, you have to mark capital T, which obviously you might have already understood is tension. Okay, and tension is always opposite to the load. So we will start from here. You can start from this effort side also. There will be tension over here, then you will have T acting here, then you will have T acting here, same T here and same T here. The reason why it is all T, T, T is because ultimately it is the same single tackle that has been used throughout. Okay, so the second part, you can, after marking in the diagram, you can say, you can write over here, marked in the diagram. Okay, so that has already been marked in the diagram. Now coming to the third part, in which they have asked the mechanical advantage. As you can see, find mechanical advantage of this entire pulley system. So mechanical advantage obviously has again the formula, same formula which we have been doing for quite some time now, load upon effort. Okay, and load, obviously you remember the process by which we calculate the value. Load is supported by 1, 2, 3, 4 tensions, so you have 4 T at the top, and effort is supported by a single T, so you have T and T getting cancelled. You have the mechanical advantage value of 4. Okay, now coming to the last part that we have over here, if DL is equal to 1 centimeter, find DE. Okay, now let me first tell you, although you obviously know that DL is the distance moved by the load and DE is the distance moved by the effort. Okay, but then the question may not always have DL and DE in it. This part can in fact be put in another alternative way also. So that alternative way would be, if the load moves up by 1 centimeter, by how much will the effort move down? Okay, so as you can see, when the person is going to pull from here, the effort, when he's going to apply the effort, he's going to apply it in the downward direction. So the movement of the effort will be downwards, whereas the load will be lifted upwards. Okay, so basically this what this line means is that if the distance moved by the load or the load moves up by 1 centimeter, by how much will be the movement on the effort side. Okay, so basically what they are asking is they want the velocity ratio value, because velocity ratio, if you remember, the formula is dE upon dl. dl you already know, dE they are asking, so if you can get VR from this combination, you can easily get your dE. Okay, so again, if you recall, we have already discussed, this is the block and tackle system, and the load is supported by 4 strands of tackle. Okay, and you have 4 pulleys overall, so your velocity ratio value will be 4. Okay, so just like you have MA as 4, you will have velocity ratio value also as 4. So this 4 becomes equal to dE upon 1, because dl value is already given as 1 centimeter. So that will give you a dE value of 4 centimeters. Okay, so you can say that if the load moves up by 1 centimeter, the effort will have to move down by 4 centimeters. Okay, actually it is the other way around, because only when you apply the effort, then the load moves up. Okay, so this is the answer to the 4th part. Now coming to the marking scheme for such a particular type of a question, you see there are 4 parts to this. Okay, so each part over here will carry 1 mark. Okay, so this question, if it comes in the board, it will carry minimum 4 marks. Okay, so one will be for just identifying the tackles, the strands of tackle. Second, just for marking the directions, correct directions of the tensions. Then the MA calculation, and then lastly the 4th part. Okay, so this will carry 4 marks overall. So you can, if you want, I can write this down over here. You will have 1 mark here, you will have 1 mark here, 1 mark over here, similarly 1 mark here, and you will have 1 mark here. Okay, so that makes an... Okay, so this is the last combination that I spoke about just now in the lecture. We have a combination of 1 fixed pulley and multiple movable pulleys. Okay, so overall this is also a combination of pulleys, just like the block and tackle system, but instead of having 2 blocks and the fixed pulleys, we have only 1 fixed pulley here, and we have a number of movable pulleys. So those movable pulleys can be 2 in number. You can have a 3rd movable pulley also in the same system. Okay, so by having such a combination, what we will see is that the number of tackles used will also change. Okay, so if you see over here, this is 1 tackle. Okay, it starts from this hook over here, goes down around this pulley, goes up, goes around the fixed pulley, and ends over here. So that is 1 tackle. So if we start marking the tension and call it T1, this will also be T1 and this will also be T1. But the tensions here and here cannot be called as T1, because this tackle is entirely a different tackle. It's entirely a different tackle from this one. Okay, so if you recall, I had told you in the previous lectures that as long as the tackle is same, the tension will be same. So here the tackles are not same. In fact, there are 2 tackles being used. So this tension in the 2nd tackle, I will mark it as T2. Okay, so, and obviously the direction will always be in a direction opposite to that of the load. Since load is trying to pull things down, you will have the tensions in the upward direction. Okay, so this is the 2nd thing that you have to very carefully note here in such a combination. Okay, so again, this setup, once the diagram gets completed, this becomes a combination of pulleys, which is in fact a machine. So for all machines we need to study the mechanical advantage, the formula for which is load upon effort. Okay, that's the common formula, the general formula that we have. Okay, so now we will start from the load side. This load, if you can see, is first of all directly supported on this T2 and this T2. So T2 plus T2 will give you 2 times T2. Okay. Now coming to this E will be equal to this single T1. Now, unlike in the previous cases, you cannot cancel this T1 and T2 because they are different. Okay, because the tackles are different, so the tension values will also be different. So they cannot be cancelled over here. So this will involve a further step where you can write T1 as it is, but this T2, if we can convert this T2 also in terms of T1, then we can get T1 cancelled. So then have a look over here back in the diagram. This T2, this particular T2 is the tension in this part of the tackle, and because of the tension in this part of the tackle, this pulley will come under strain. Okay, because of this tension T2, there are these tensions that have developed. Okay, so in fact this T2 is resulting in these two T1s. Okay, so what I can do is I can write T2 equal to T1 plus T1, so that makes it 2 times T1, because ultimately it is this tension which is getting supported by these two tensions directly, just like this load was getting directly supported by these two T2s. Similarly, this T2 is getting supported by these two T1s. Okay, so T2 becomes 2 T1. Now replacing this over here, in place of T2 I can write 2 times T1. So this will become 2 2s are 4 T1 upon T1. Now you can see T1 and T1 will get cancelled. So this comes out to be 4, which can be further expressed as 2 raised to the power 2. Okay. Now there is a reason why I have put it like that. When you will calculate, let's say for example, this was the case where one fixed pulley was there, 2 movable pulleys were there. Okay, so in case of 2 movable pulleys, the power has come out to be 2. Okay, similarly, now this can be a sort of a homework for you. You can go back after watching this lecture and you can draw a diagram having 1 fixed pulley and 3 movable pulleys. So in case of 3 movable pulleys, you will find that you will have the MA value as 2 to the power 3. Okay, where this 3 will denote the number of movable pulleys in that system. Okay, so if we generalize, we can write MA value will be 2 raised to the power n, where n is the number of movable pulleys. Okay, so this is the generalized version that I have written. Okay, that's the generalized formula. Generalized formula. Okay, so in this particular case that we have discussed, what is the value of n? The value of n is number of movable pulleys. So in this particular case, movable pulleys are 2, so that is why 2 to the power 2. If you include a third movable pulley also, by using the same type of calculation, you will get 2 to the power 3. Okay, so this is what is different in this particular case. Similarly, when we talk about VR value will also come out to be 2 raised to the power 2. I am again talking about this particular combination. Okay, so this 2 is again the number of movable pulleys in this particular case. Okay, logically also you can try to understand how this value came out to be 2 to the power 2, that is 4. You see, if this load is to move up by 1 centimeter, okay, so because this load moves up by 1 centimeter, this pulley will try to move up by 1 centimeter. So in this movement of 1 centimeter, 1 and 1 centimeter will get released on both sides, resulting in an overall release of 2 on this side. So when there is a movement of 2 centimeter up here, when there is a movement of overall 2 centimeter up here, there will be a subsequent movement of 2 and 2 that makes it overall 4 centimeter. That 4 centimeter gets carried onto this side. So this will move by a distance of 4 centimeters. Okay, so you can see that DL is 1 and DE is 4. So velocity ratio value is DE upon DL, so that comes out to be 4 again. So you can now directly write VR, which is the velocity ratio value, will also be equal to 2 raised to the power 2. Again, the last thing that we have is efficiency, which is MA upon VR. So we have MA as you can say directly 4 for this particular combination. The MA value is 4 and the VR value also is 4, 2 raised to the power 2, which is 4. So we have an efficiency of 1 or 100%. Again, I do not need to tell you that this is the ideal case scenario. That is why efficiency has come out to be 100%. In all practical cases, efficiency value will be less than 100%, and that will only be possible when MA drops below 4. Okay, VR will not change. VR will remain 2 raised to the power 2. MA, it is MA which will reduce because of a number of reasons which I have already explained. We generally neglect the weight of these movable pulleys, but that weight is not zero. It is never practically zero. Okay, so we are basically not incorporating the weight of the movable pulleys. That is why in ideal case scenarios we always get efficiency as 100%. Okay, so based on today's lecture, now you must have had a complete idea of what are the different possible combinations of pulleys and the way in which you are supposed to calculate MA, VR and so on. Okay, so you can be given questions in which you will have values. You can simply put them in the formula. Then you will obviously have to have a lot of practice of such cases, of drawing tensions, of marking the correct directions, of drawing the tackle, how to draw the hook, and how to draw the fixed support and all these things. Okay, so with this we come to an end to machines. Next we will be starting with light. Okay, thank you.